This is the 19th lecture on DSP, and the topic for today is test for stability using all pass functions. Stability we shall test for an arbitrary IIR transfer function. All pass functions will be a via media. This again shows the importance of all pass functions in DSP. In the last lecture, we showed that these two transfer functions h naught z and h1 z, which is half of the sum and difference of two all pass functions, form an extremely important complementary delay complementary as well as all pass complementary as well as power complementary functions. And we defined a frequency called the crossover frequency, at which either of these have a magnitude equal to 1 by root 2. Magnitude squared is half. That's why I paused. And then we showed that a very simple realization is possible. All that you have to realize is A0 and A1, two all pass functions. And we took a particularly simple and interesting example of A0 being equal to 1 and A1 being equal to a first order all pass, which gives a very versatile realization of several kinds of filters and also a magnitude complementary pair by taking h naught squared and h1 squared. Then we introduced the concept of digital two pairs, and we showed how they can be represented by a transmission matrix and a chain matrix gamma, and we showed how cascades can be of two different types, transmission cascade and chain cascade, in which the respective parameters multiply each other to get the overall transmission or chain parameters. And then we started stability testing, and we took a second order transfer function h of z equal to n of z by d of z, where d of z being a second order can be written as 1 plus d1 z inverse plus d2 z to the minus 2. We want to test the stability without determining the roots of this function, the denominator, which will become the poles of h of z. Now, if I write this as 1 minus p1 z inverse multiplied by 1 minus p2 z inverse, that is p1 and p2 are the poles, then we require for stability magnitude p1 less than 1 and magnitude p2 also less than 1. And if we write in this form, obviously p1 plus p2 shall be equal to minus d1 and p1 p2 shall be equal to d2. Now, for stability, since p1 and p2 both have to be less than 1 in magnitude, therefore d2, the magnitude of d2 should be less than 1. Agreed? Because the magnitude of d2 is simply the product of the magnitudes of p1 and p2. It should be less than 1. In other words, in a parameter plane, that is, if we plot d1, if we plot d2 versus d1, then magnitude d2 less than 1 means d2 should be confined between minus 1 and plus 1. Agreed? Minus 1 and plus 1. Now, there are two possibilities. The poles can be real or poles can be complex. In either case, P12 shall be equal to minus d1 by 2 plus minus square root of d1 squared minus d1 squared by 4 minus d2. If the roots are complex, then obviously d1 squared by 4 should be less than d2. Okay? First let us see complex roots, complex poles. The condition is that d2 should be greater than d1 square by 4. Agreed? In other words, if I plot the curve with an equality sign here, that is d2 equal to d1 square by 4, if I plot this, then d2 should be above this curve. All right, d2 should be above this curve. Not only that, since it is d1 squared and d1 is a real quantity, it could be positive or negative, but d2 therefore should be greater than 0. Agreed? Therefore, if we go back here, if we go back to this slide, d2 equal to d1 square by 4 is a parabola. When d1 is 0, d2 is 0. When d1 is plus 2 or minus 2, it is equal to plus 1. Therefore, these are 2 points, and you can draw the parabola through this, where this is plus 2 and this is minus 2, minus 2. Therefore, if the roots are complex, then they should be contained in this cup. Agreed? The hatched region represents complex poles. That is, if d1, d2 in the parameter plane, the point d1, d2 is here, then you know it is a complex pair of poles. Not only that, if the poles are complex, if the poles are complex, that is P12 shall be equal to alpha plus minus j beta. Okay? Then magnitude P1 squared shall be equal to magnitude P2 squared shall be equal to P1 P2. Agreed? And that is equal to d2. Right? P1 P2 is equal to d2, and that is equal to alpha squared plus beta squared. Correct. So, we have taken care of complex poles. Now, let's see what real poles shall give us. If the poles are real, this means that d2 should be less than d1 square by 4. Agreed? And where are the poles? P1, let us say this is equal to minus d1 by 2 plus square root of d1 square by 4 minus d2, and P2 is equal to minus d1 by 2 minus square root of d1 square by 4 minus d2. Agreed? We want, since these are real, we want their mod to be less than 1 for stability. Now, which one of these can exceed 1? Not P2. P1. P2 is, this is negative, this is negative. Even if d1 is negative, d1 square by 4 is positive, and therefore this can exceed 1. In other words, we want P1 to be less than 1. P2 can go beyond minus 1 because both are negative, and if d1 is positive, both are positive, d1 by 2 and square root of this. Therefore, this should be greater than minus 1. Is that clear? In other words, P1 and P2 should be confined within this region. One can be positive, one can be negative, both can be negative, both can be positive, all right, but they must be within this part of the real line. And P1, if we satisfy these two, that is P1 less than 1 and P2 greater than minus 1, then our job is done. Agreed? So, let us see what these conditions lead to. Minus d1 by 2 plus square root of d1 square by 4 minus d2, this should be less than 1. That is, square root of d1 square by 4 minus d2 should be less than 1 plus d1 by 2. If I square both sides now, then I get d1 square by 4 minus d2 should be less than 1 plus d1 square by 4 plus d1. Therefore, d2 therefore, d1 square by 4 and d1 square by 4 cancels. If I change the sign, d2 should be greater than minus 1 minus d1. Agreed? d2 should be greater than minus 1 minus d1. In a similar manner, if I take the other one, that is, let us do that, minus d1 by 2 minus square root of d1 square by 4 minus d2 should be greater than or less than? Greater than minus 1. Therefore, minus square root of d1 square by 4 minus d2 should be greater than minus 1 plus d1 by 2. Now, if I square both sides, then d1 square by 4 there is a problem of sign. So, let us change the sign. That is d1 square by 4 minus d2 should be less than 1 minus d1 by 2. Pardon me? Square of this. Let us square this. So, I get d1 square by 4 minus d2 less than 1 plus d1 square by 4 minus d1. This cancels, and therefore, this condition is that d2 should be greater than d1 minus 1. Now, if I plot this with an equality sign, I shall get a straight line. And what was the other condition? d2 greater than minus 1 minus d1. Once again, if I plot this with an equality sign, then we shall get a straight line. Let's see this straight line, d1 and d2. If d1 is 0, then d2 is minus 1 with an equality sign. If d1 is 0, d2 is minus 1. If d1 is minus 1, then d2 is 0. And therefore, if we go to this same diagram, d1 0, d2 is minus 1, let me use another, d2 is minus 1, and the other one is d1 minus 1 and d2 is 0. So, minus 1 is somewhere here, and therefore, this must be the straight line. 2 points are good enough to draw a straight line. In a similar manner, the other straight line will be this one. Okay. So, this triangle, the red outline triangle, this is the parameter, part of the parameter plane in which the second order transfer function shall be stable. Okay. They shall be stable. In addition, so this is called the stability triangle. for a second order transfer function, second order IIR transfer function. Okay. This is the stability triangle. In addition, if it is within the hatched area, then the poles will be complex. If not, then they shall be real. If D1, D2 point is outside this triangle, the system would be unstable. But this is doing too much with a very simple transfer function, second order. You can always find the roots and find whether it is stable or unstable, whether the roots are real or roots are complex. But then this stability triangle is useful in a different context, in studying the quantization errors in a digital signal processor, and therefore I thought we must do this at this stage, second order. So you get some experience. Then we have to answer this question, what do we do if we have a general transfer function, let us say h m of z is equal to d m of z, mth order, and n m of z, where d m of z, testing for stability means we test for the roots of d m of z and find whether all the roots are inside the unit circle or not. Let d m of z be written as 1 plus d 1 z inverse. This is the discipline we follow. In the numerator, the constant term is 1 plus d 2 z to the minus 2 plus etc. plus d m z to the minus m. All right. Instead of finding the roots, we go through via media of an all pass function. In other words, what we do is we construct from this, the first step, we construct from this an all pass function with the same denominator d m of z, and the numerator therefore shall be z to the minus m d m z inverse. Okay? That is, the coefficient shall be in reverse order. In other words, if I write this specifically, 1 plus d 1 z inverse plus etc. d m z to the minus m, and we shall start here from d m, and then I shall get d m minus 1 z inverse plus etc. plus the last term would be z to the minus m. Coefficient will be 1, because this will go here. Agreed? Now, if the roots of DMZ are, let us say, pi's, I equal to 1 to m, that is, if dpi is equal to 0, then pi's are the roots of DMZ. Then for stability we require magnitude pi less than 1 for stability, which means that dm, what is dm? Dm is the product of the roots, the constant term, the coefficient of z to the minus m. Is the point clear? This term must be the product of the roots. Okay. So, dm, which is equal to minus, which is equal to pi, continued product pi, I equal to 1 to m, dm must be constrained for stability, since magnitude pi is less than 1 all I, therefore dm should be less than 1. Okay. For consistency in notations, you notice that dm is equal to am of a particular value of z. What is the value? No. That is why I asked you. Look at this. I want only dm. So all other terms must be 0. Infinity. That is correct. So dm is am infinity, and for reasons to be made clear, I shall denote it by small k subscript m. They are identical in this stage, but they are not so as we proceed ahead. So, for stability therefore, for stability Km squared, dm is a real quantity, positive or negative, but its squared is a positive quantity, that must be less than 1. This is a sufficient condition or necessary condition. This is necessary but not sufficient. It is a necessary condition. Okay? So, let us say that AMZ, let us assume that AMZ is stable with Km squared less than 1. All right. Let us suppose now we are entering into a proof, and therefore, we shall introduce induction, all kinds of reasoning. Okay. Let us suppose that AMZ is stable with Km squared less than 1. The next step is find a lower order all pass, order less by 1, by using the relationship what we do is we form a transfer function one order less am minus 1z. Again we aim at an all pass function. We shall show that it is all pass. Okay. What we form is am minus 1z is amz minus km, km is the same as dm, divided by 1 minus km am of z. Okay, which means that it is the same as amz minus dm divided by 1 minus dm am of z. Let us see what this transfer function is. We have arbitrarily put here m minus 1, we will show that the order is m minus 1. Okay. Now, if I substitute for am, then I can write this as n m minus 1 z divided by d m minus 1 z. Again we shall show that the numerator is m minus 1th order and the denominator is also m minus 1th order. Now, if I substitute for amz, then what I get is n m minus 1, the numerator, n m minus 1 of z shall be equal to amz minus dm, and therefore, the numerator of amz, which is dm plus, I beg your pardon, I made a mistake. I have a multiplication of z here. Would you correct this? I multiply by z. Numerator amz minus km is multiplied by z. Okay. Therefore, n m minus 1 shall be equal to z numerator of amz dm plus dm minus 1 z inverse plus etc. plus z to the minus m, all right, minus dm multiplied by the denominator of am, which is 1 plus d1 z inverse plus etc. plus, have I made a mistake? No, not yet, dmz to the minus m. Okay. So, this I can write as see, one of the terms cancels here. Yes, have I made a mistake? I said not yet. You see, what I have done is I have written am equal to nm divided by dm. So, this is okay.
Whole should whole divided by d.
No, this is I am written only the numerator. I have written only the numerator, not the denominator. Now see, this dm and this dm cancel. Agreed? Then I have.
So even then an is nm divided by dm, and you have multiplied dm by denominator part. Therefore, it should also have a denominator.
Now, okay, amz minus dm is equal to nm divided by dm minus small dm. Therefore, nm minus 1, dm shall cancel from the denominator also. I am writing the numerator polynomial only. Dm shall cancel from the denominator. Well, since there is a confusion, let me not skip the algebra. Let me do it. What was our function? Our function was am minus 1z equal to z times amz, that is nm by dm, minus small dm divided by 1 minus dm nm divided by dm. So, if I simplify this, I get z nm minus dm dm divided by dm minus small dm nm. Agreed? And this is n m minus 1 divided by d m minus 1. Agreed? Therefore, n m minus 1 is given by the numerator of mth order minus dm multiplied by the denominator, and this is what I did here. Okay, so dm and dm cancel, and what do I get after simplification? You see, what happens is the coefficient of z inverse shall be dm minus 1 minus dm d1, but there is a multiplication by z, and therefore the constant term in the numerator shall be dm minus 1 minus dm d1. Therefore, what I get is n m minus 1. We have to be very careful. It's a little involved proof, but it makes life so comfortable in testing and all, in testing any arbitrary IIR transfer function. So, you must follow the proof carefully. So, this would be dm minus 1 minus dm d1 plus the next term would be dm minus 2 minus dm d2 z inverse. Agree? Plus etc. What will be the last term? 1 minus dm squared, and the power of z shall be minus m minus 1. That is correct. So, the numerator is indeed an m minus 1th order polynomial in z inverse. Okay? So, our m minus 1 subscript is justified. In a similar manner, you can show that dm minus 1z, I will simply write it down. Now, the constant term would be 1 minus dm squared, okay? Because what do I get here? Dm, the constant term here is 1, and the constant term here is dm. So, dm multiplied by not the constant term, the coefficient of z to the minus m. I beg your pardon. The constant term is nm is dm. Constant term is numerator of am is dm. So, dm multiplied by dm is dm squared, 1 minus dm squared plus d1 minus dm dm minus 1 z inverse plus etc. plus z to the minus m term shall cancel. This will cancel. So, I shall get dm minus 1 minus dm 1 multiplied by z to the power minus m minus 1. And you see, if this polynomial is put over this polynomial, we get an all pass function. Isn't that right? Therefore, a m minus 1 z is all pass, and if we follow the same discipline, and make the constant term here as unity, constant term in the denominator as unity, then we will have to divide both numerator and denominator by 1 minus dm squared. Agreed? Then I shall get 1 plus d1 minus dm minus 1 divided by 1 minus m squared, and so on and so forth. Agreed? Therefore, a m minus 1 z shall be of the form 1 plus d1 prime z inverse plus d2 prime z to the minus 2 plus etc. plus d subscript m minus 1 prime z to the minus m minus 1, and the numerator shall be dm minus 1 prime plus dm minus 2 prime z to the minus 1 plus etc. plus z to the minus m minus 1. It is an all pass function, okay, where obviously the relationship is di prime, the coefficients are di minus dm d m minus I whole divided by 1 minus dm squared. I going from 1 to for the primed, the order is m minus 1 to m minus 1, and this is the golden relationship. This is the recurrence relation, but we still have a long way to go before we accept this recurrence relation. Okay, what was our assumption? That AMZ is stable and Km squared is less than 1. Now let us see, is AM minus 1Z stable? That is the question. If it has to be stable, you remember AM minus 1Z is equal to, what was the relationship? AM Z minus Km divided by 1 minus Km AM Z multiplied by Z. I seem to be dropping this term all the time. Okay. All right. Now, if we have proved that if AMZ, let's go back and take a stock of the situation. We have proved that if AMZ, how did you construct AMZ? With the same denominator as that of the given transfer function to be tested. We have proved that if AMZ is stable and Km squared is less than 1, then AM minus 1Z is an m minus 1th order all pass function. Now we have to show, we want to show that AM minus 1Z is also stable. Let us see if it is or not. Now suppose AM minus 1 of Qi is equal to 0. No, I beg your pardon. Let Qi be a pole of AMZ. We are now testing the poles of, no, not AMZ, AM minus 1Z. Okay. In order to prove that AM minus 1Z is stable, we have to look at its poles. Okay. And the poles are the zeros of this, the denominator. How many poles? M minus 1. We have chosen an arbitrary pole Qi. Then at Qi, the denominator must be equal to 0, that is 1 minus Km Am of Qi is equal to 0, which shows or Am of Qi is equal to 1 by Km. Therefore, Am of Qi magnitude is equal to 1 by Km magnitude. Km could be positive or negative, but Km squared by hypothesis is less than 1. Therefore, this must be greater than 1. Okay? We have also shown that if AMZ is a stable all pass function, then its magnitude is greater than, equal to or less than 1 for magnitude Z less than, equal to or greater than 1. Agreed? Therefore, if AMQI, we assumed AM to be a stable function. So, if AMQI is greater than 1, then QI must be less than 1. Therefore, magnitude Qi is less than 1. What are Qi's? Poles of Am minus 1Z, and therefore Am minus 1Z is stable all pass. Okay? That is the end of part 1. Part 1 says if AMZ is stable and Km squared is less than 1, then Am minus 1Z is a stable all pass function. Now we prove the reverse. That is, we assume that AMZ is stable all pass. We assume that AMZ is stable all pass and Km squared is less than 1. Km squared less than 1 was a necessary condition but not sufficient. Alright. So, the converse proof will consist of let Am minus 1Z be a stable all pass and let Km squared be less than 1. Then prove that AMZ is a stable all pass function. Then these two will constitute necessity as well as sufficiency, and that will constitute the core of the test that we are going to learn. So, what we are going to prove now is if Am minus 1Z is stable all pass, then and Km squared is less than 1, then Am of Z is stable all pass. This is what we have to prove. Now let us see if we can do this. Now our defining relationship was Am minus 1Z was equal to, remind me if I drop that factor Z, Z times Km, no, Am of Z minus Km divided by 1 minus Km Am of Z. This was our defining relationship for finding Am minus 1. Now, what we have to do now is to find Am in terms of Am minus 1Z, and therefore cross multiply and simplify. The relationship is Am minus, no, I am sorry, AMZ is equal to Km plus Z inverse Am of Z, no, Am minus 1Z. AMZ, let us write it again, equal to Km plus Z inverse Am minus 1Z divided by 1 plus Km Z inverse Am minus 1Z. We have expressed Am now in terms of Am minus 1. Okay? Agreed? Now to prove that AMZ is all pass is trivial. Isn't that right? That's what we started with. AMZ was an all pass function. So, all we have to prove is that AMZ is stable under these conditions. That is AM minus 1Z, this is stable, and Km squared is less than 1. Agreed? What did we assume? Did we assume the poles of AM? Did we put a symbol? No. Let P sub I be a pole of AMZ. How many? Capital M number. Okay. Then if P sub I is a pole of AMZ, now look at the beauty of the proof. Therefore, 1 plus Km P sub I inverse A m minus 1 P sub I should be equal to 0, right? Therefore, therefore, Pi inverse Am minus 1 Pi should be equal to minus 1 over Km. Agreed? If I take the magnitudes on both sides, then Pi inverse Am minus 1 Pi should be equal to 1 over Km, that is less than 1. Is that okay? Less than 1 or greater than 1? Do not allow me to make a mistake. This is greater than 1. Therefore, magnitude Am minus 1 Pi is greater than magnitude Pi. All right? Okay? No, this is okay. There is a Pi inverse and no, it should be greater than Pi. Should be greater than Pi. Agreed? Now, Am minus 1 Z is a stable function. Agreed? So, Am minus 1 Z, this is the crucial point of the proof. I want your full attention. If this is stable, then Am minus 1 Z is greater than equal to 1, I beg your pardon, less than equal to 1 for mod Z greater than equal to 1. Okay? If Pi magnitude is greater than equal to 1, if Pi magnitude is greater than equal to 1, let me write it down, greater than equal to 1, then Am minus 1 Pi magnitude should be less than equal to 1. Agreed? But this shows that Am minus 1 Pi should be greater than magnitude Pi. That is, it should be greater than 1. Therefore, these two are contradictory. Therefore, this cannot be allowed. Is that clear? The proof is by contradiction. You see, if Am minus 1, let me repeat, if Am minus 1 Z is stable, then this condition must be true. Therefore, if magnitude Pi is greater than equal to 1, then Am minus 1 magnitude should be less than equal to 1. On the other hand, this relation shows that it should be greater than magnitude Pi. That means it should be greater than 1. So, these two are contradictory, and therefore, magnitude Pi must be less than 1. In other words, we have proved that if am minus 1, the derived function, is stable, then the original function must also be stable. So, we now state the core of the test, that is, it says that if AMZ is stable all pass, then AM minus 1Z is also stable all pass. Okay? Is also stable all pass. This is necessary as well as sufficient. So, the testing simply amounts to this. What we say is, if AMZ is stable all pass, then Km squared must be less than 1. Then we derive the lower order transfer function AM minus 1Z and look at Km minus 1 squared. What is this equal to? Dm minus 1 prime. Agreed? Km minus 1 is simply dm minus 1 squared. That should also be less than 1. Okay? And then by recursion we form am minus 2 and we test for Km minus 2. That should also be less than 1, and we proceed up to the first order, that is K1 should also be less than 1. So, this is the stability test. Given the transfer function, is the proof clear? Is the logic clear? Why it is so? It is very important that you understand the logic. It is one of the most beautiful theorems in DSP, which shows how to avoid all these root finding. It is a little bit of exercise, but that recursion relation, you see, you do not have to find all the transfer functions. All you have to find are the polynomials, the denominator polynomial. And denominator polynomial means you have to find the coefficients of the polynomials, and therefore that relationship di prime relating to di is the only one that you shall use in the process. Okay? And what you will do is you will find Km minus 1 up to K1. Why don't you go to A0? Why do you stop at A1 of Z? A0 is trivial. What is A0 equal to? 1. The 0th order all pass function is 1. Now, enough of theory. If you have understood this, we will take a detailed example. The example that we take is you are required to test whether this transfer function 1 by 6 plus 5 z inverse plus 4 z to the minus 2 plus 3 z to the minus 3 plus 2 z to the minus 4 plus z to the minus 5. You are required to find whether this is stable or not. The numerator, for simplicity, numerator is irrelevant, isn't it? Numerator can be 1 or any other function. So, the first thing you do is form an A5Z. Now, you must be careful. Intentionally, I have used a 6 here. You must make these two 1. So, your A5Z denominator would be 1 plus 5 by 6 z inverse plus 4 by 6 is 2/3 z to the minus 2 plus 3 by 6 is half z to the minus 3 plus 1/3 z to the minus 4, is that right? 2 by 6 is 1/3 plus 1/6 z to the minus 5. This is our denominator. Okay? So, and the numerator you can write it down. Okay? Numerator you can write it down 1/6 plus etc. But this need not be written, because all we are concerned with is the denominator coefficients, and you see that K5, magnitude K5, which is equal to 1/6, Well, k5 squared is 1 by 36 is less than 1. Why do you take squared? Because the last coefficient may come positive or negative. Okay, this is trivial here, it is positive. So, k5 squared is 1. First condition is satisfied. If this was not so, then you did not carry out the test. Agreed? Okay. Then to find A4Z, let A4Z denominator be 1 plus d1 prime z to the minus 1 plus d2 prime z to the minus 2 plus d3 prime z to the minus 3 plus d4 prime z to the minus 4. Okay, and the numerator you can construct. Now here our interest is only d4 prime, but to find d4 prime you have to go through finding all of them. Agree? Because the next one shall require the values of d1 prime, d2 prime and so on and so forth. So we use the formula di prime is equal to di minus dm. What is dm here? 1/6. Agreed? Then d m is 5. So 5 minus I divided by 1 minus dm squared. Dm is, so it would be 1 by 36. That is equal to, simplify this. I am through this example I am also telling you how to proceed with numbers. Okay, simplify this. Don't leave it like this. You write this as 36 by 35. Life would be much simpler. di minus d5 minus I divided by 6. Suppose I want to find out d1 prime, then 36 by 35. What is d1? 5 by 6, right? d1 is 5 by 6 minus d4. What is d4? 1/3, so 1 by 18. Simplify it as such and put it in the form of a fraction. As long as possible, retain this in the form of a fraction. This simplifies to 4 by 5. My calculation, I do not guarantee, you must verify. Okay? And similarly, you put I equal to 2, I equal to 3, I equal to 4 and so on. And my calculation shows that d2 prime is 6 by 10, that is 3 by 5. d3 prime is 4 by 10, so 2/5. Is 2/5 equal to 0.4? Yes. Okay, and d4 prime is equal to 1/5. The same formula. Okay. Now therefore k4 magnitude squared, no, not magnitude squared, k4 squared is equal to 1 over 25, which is less than 1. The test has not failed yet. Okay. So we are encouraged to go to the next step, that is, you have to compute A3. Now you don't have to go through writing A3, or it's better, write d3 of z as equal to 1 plus, now I am running out of symbols, so I shall use a double prime, d1 double prime z inverse plus d2 double prime z to the minus 2. You can divorce capital A3, you are only concerned with the denominators, because numerator you can construct, plus d3 double prime z to the minus 2 and z to the minus 3. I have written correctly, spoken wrongly. And the formula now shall be di double prime, do not confuse, di double prime shall be equal to di prime minus d4 d4 minus I prime d4 prime 1 minus d4 prime squared. What was d4? 1 5, so 25. Write this as 25 divided by 24 di prime minus d4 minus I prime divided by d4 prime is 5, so 5, and calculate the coefficients. My calculation gives d1 double prime is equal to 3/4, d2 double prime is equal to half, d3 double prime is equal to 1/4, and that's it. Therefore, K4 squared, K3 squared, which is 1/16, is less than 1. The algorithm is clear now.
Yes.
There are many shortcuts. You don't have to do the algebra. All you have to do is to find the coefficient, but you have to keep a track. Now, if we continue the test, I have completed. If we continue the test, then you get K2, I beg your pardon, K2 squared is equal to 1/9. Show. From the third order, you find the second order. Show that K3 squared is 1/9. This also verify my calculation. And K1 squared is 1/4. This also is less than 1. I have chosen the coefficients in such a manner that life remains simple. You may not get this. You may get something like 29 by 358 or something. Keep it, have patience, keep it like this, and spend a little bit more time to be able to say confidently at the end of the test whether the function is stable or unstable. And if it is only testing the function, then in all probability you might have to leave in between, because if one of the case comes out to be greater than 1 in magnitude, then the rest does not have to be performed. But if you are designing a filter, then you better do the test twice or thrice, okay, so that you are absolutely sure that the given function is stable. Okay. Number 2, this di prime equal to di minus dm minus I 1 minus dm squared can be, you can write a very simple program to compute this, and all you have to do is change m, and you have to keep track of the primes. Well, if it gets complicated, and you use the 26 alphabets. Use the symbols A, B, C, D, and so on and so forth. And if you exhaust that, then you go to alpha, beta, gamma, delta. Because if it is a 6th order, for example, di 6 primes, that's going to be difficult. What the books is di 6, but this is also sometimes confusing. It may be taken as the power. Computer is a stupid fool. I mean, it works the way you ask it to do. Suppose it confuses it as a power, then your test is gone. We'll stop here and take questions.